All right, so this is the New Keynesian IS curve. One thing, by the way, I forgot to mention on the last slide. Actually, let me just flip back one slide here and show you. So it was hidden under the foot of the slide. Is that everything in these equations is going to be implicit to steady state levels. So what we really mean here by yt, even though it's not written this way, is we mean the log difference between yt and the steady state value of y. Okay, and the steady state value of y, there's no expectations here, so it's very easy for us to bring that into the expectation terms as well. So for instance, what we mean by this term here is actually the expectation of the log of yt minus the log of y0, et cetera, et cetera. So that's just something to remember. I needed to say it because I'm going to use that as a step in the algebra in the next slide. So anyway, now onto the New Keynesian IS curve. If you remember, in many of the models we've derived in this class that we've sort of explored or analyzed in this class, we end up with an Euler equation that's going to relate. Let me turn my cursor here into a pencil so I can point things out. So it's going to relate consumption today to consumption tomorrow. And you may recall that in the real business cycle model, we had this complicated situation where we couldn't isolate the consumption tomorrow from the interest rate or the rate of return tomorrow. Okay, so we're going to start with this equation, all right, and then we're going to kind of make a couple of small changes to it. That's going to make it easier for us to analyze in this model. So the first thing is we're going to assume that the only factor is labor. There's no capital accumulation in this model. So we're going to have in the back of our minds, we're going to have a representative agent. And since everyone is exactly the same, they all have the same amount of labor every day. One more thing. There's no real savings. There's no saving technology to allow us to take output today and bring it to tomorrow. Since that's the case, consumption today is going to be exactly equal to output today. We don't have a savings technology to let us accumulate any sort of savings or transfer production between times in this model. It's an assumption, but it's going to make our lives a lot simpler because we can just replace C with Y. Okay, so that's the first change. The second change between this first equation and the second one is you'll notice that the expectation came off of this RT term. So, formally you can see that instead of writing t plus 1 here, we just wrote t, which is, and then, the expectation of a variable that has a subscript t at time t, it's just, we know what that is. The information about what that variable is we already have, so we can just take the expectation out. So that's the cheating formal way of saying it. But what we mean by this in this model is that this is not a rate of return on capital investments the way it was in other models we've looked at, for example, the real business cycle model. Rather, this is just some rate that's set by the government. Okay, and there's little else to say about it. The government chooses it. The central bank chooses it. So it's something they announce and they can commit to today. So the interest rate is simply a policy variable, if you like. So there's no expectations. There's no uncertainty about what that will be. You know what your rate of return will be. Okay. You might say, wait a second, didn't you just tell me that there's no saving in this model? So how can there be a rate of return? That doesn't make any sense. Well, that's true. Basically, the level of output is going to be such that at the particular interest rate, people don't want to save. So it's going to be, again, this sort of equilibrium concept. The thing that's a little bit different in the model that we're looking at today, I hate to do this, but let me just flip back one slide. The thing that's a little different is that the government is going to choose this thing, the interest rate. This is the expected output tomorrow. So that's not something the government chooses, but it's also not something that people choose. That's just something that's given. Remember, there's no savings. So basically, how do we make this interest rate such that people don't want to save? Well, basically what's going to happen is people are going to, or the output level today is going to adjust. Implicitly, people are choosing how much they want to work. Okay. So rather than having sort of output tomorrow and output today fixed, and then you choose the interest rate that is going to rationalize those levels of output, here we've got the output tomorrow fixed. We've got the interest rate fixed by the government. So then people are going to choose how much output there is today in order to rationalize the interest rate and the output rate tomorrow. So it's a little bit different than what we've done before, but it's a similar flavor, and it's still the same Euler equation. Okay, so that's why there's no expectations. All right, so we've made those two changes, and already you can see that this is looking very close to what we need to derive, which is a relationship between yt plus 1, and rt. Okay. So as I just said, we're going to have everything here relative to steady state levels. There's a little bit of notational issues here, but bear with me. So basically, we can just divide this equation by the steady state version of this equation, which is here. And I've got little zeros here on the steady state values. Okay, and then when I have this tilde, this big tilde over something in an equation, what I mean is just the relative sort of output today relative to the steady state value, or in this case, marginal utility of output today relative to marginal utility of the steady state value, if that makes sense. Okay, so let's take logs here. Okay, so all we're doing is taking logs of both sides of the equation. Oh, I forgot to mention one important thing on this last slide. Sorry for clicking up and down so much. But notice that this beta disappeared. The beta disappeared down here because we're taking this relative, this ratio. So we're just dividing beta by beta. Okay, so we take logs of that equation from the last slide and we get this expression. Okay. Nothing else to say about it except one thing, which is we're going to replace this 1 plus r with just r. So log has a property, which is, actually, I should do this. Okay, so this is the expression log of x, and this is x. Then log of 1 is equal to 0. And it turns out that right at this point, the slope of the log line here is also 1, right? It makes sense because we know that the derivative of the log function with respect to x is just 1 over x, right? So at 1, the derivative is 1. So for small values of an interest rate, where 1 plus r is very close to 1, then because of this slope property, we know that the value of this log is approximately RT. It's actually kind of an interesting, it's kind of a cool thing, because the log of 1 is 0, right? So since the slope here is 1, then basically the log of 1 plus x, where x is small, is going to be just approximately equal to x. And the approximation gets worse and worse the farther away from 1 you get. But anyway, that's how we got that little number there. Okay, so we've got one interesting thing here. That's good. One more thing we need to plug in CRRA into these marginal utilities to figure out how we get to this expression down here. So you'll recall that CRRA utility looks like this. It would be y1 minus theta divided by 1 minus theta. Okay, so then the marginal utility would be y to the power negative theta. All right, so far so good. Now let's think about this relative version. So u prime, that's right, what's the right way to do this? So u prime yt tilde is equal to yt negative theta divided by y0 negative theta, okay, which is just equal to yt divided by y0. Let's call that yt tilde to the power negative theta. All right, so then let's take the log of this thing. See, we're getting very close here. Let's take the log of that. So the log now of u prime yt tilde is going to be equal to negative lambda log yt tilde. All right, and then let's just define log yt tilde as just tilde little y, okay? Okay, so we get this, and then you can see that now. Let's just rewrite this expression now with our derivation here. So then we're going to get negative lambda little yt tilde is equal to, and this expectation is going to work exactly the same way because y0, there's no expectation here. It's just a number. So we can just write the expectation of little y t plus 1 tilde times negative theta plus r t tilde. It should be plus here as well, right? Okay. I'm just going to pause here for 1 second. Hey, sorry about that. I just realized as I was writing out this equation that there's a little trick here. So as I was deriving it, so you can see that I don't know if you caught it when I just did it a second ago, but here you can see that I'm taking the log of the marginal utility, and then over here there's that you can see that the log is outside of the expectation, and then down here the expectation is outside of the log. So that's not actually totally innocuous. So you know, the log is a concave function. So when you take the expectation of a concave function, it's kind of an average of. Just think about it this way. Let me just draw it here. So if you take the expectation of a concave function, it's like you're taking an average of the function at two values. Okay, so it's like that. Now suppose that the expectation of these two numbers, you know, is I should put it this way. Okay, so we're taking the expectation of the log. It's like an average of this point and an average of that point, and you know, so maybe the average is here. Okay. Whereas if we take the expectation first and then we take the log, then the average would be here. So basically, you're going to get a different number if you take the expectation first or if you take the log first. So as I was driving this, I was kind of getting confused, and then I actually just kind of went back and checked the textbook, and they say that this equation is similar to what they use in 6.1 and 7.1, and in those two chapters they don't actually have any expectations. In chapter 6 part 1 and chapter 7.1 there's no expectation, so they can derive this equation exactly if there's no expectation. But when you put the expectation in, I actually think there's a little bit of hand waving here because it doesn't totally match. Now I can imagine I think you could make an argument that as long as yt and yt plus 1 are not too far away from each other, or I should, maybe that wasn't quite the right way to put it. As long as yt plus 1 and the steady state level of yt plus 1 are not too far away from each other, I think you could argue that this approximation is okay. But I'm not going to do that. I'm just going to go with what's in the textbook, and just remind you that there's a bit of hand waving going on here. All right, so let's divide both sides here in this last equation by negative theta, and you'll see that I'm actually going to end up with yt tilde is equal to this expectation of yt plus 1 tilde minus 1 over theta times rt tilde. And then here, there should be a minus as well, and there should be a 1 over theta as well. Well, I didn't really need to, I shouldn't have even put this one up here, but I'm just going to erase it because that u isn't actually part of the Euler equation. It's just something we add in at the very end, so we can add it in however we like. I was going to say that it doesn't matter if it's negative or positive, since it's going to be some symmetric white noise distribution around 0, so it doesn't matter if you switch it one way or the other. But I think it's easier just to make the point this way. First we derive this expression, and then we add in this little productivity shock. So that is it for the Lucasian IS curve, and next we're going to talk about the Phillips curve.